So yeah, thank you for the introduction. So as the title suggests, I'm going to present a solution that we propose in this paper, centered around MDE and a domain-specific language to help data scientists deploy monitoring workflows to monitor their performance of ML models over time. So in this talk, I'm going to, first of all, motivate the problem space a little bit and explain just some concepts from the data science domain, so it's clear why we do what we do. Then I'm going to describe the proposed solution, and finally I'm going to show the results of an empirical study that we conducted. So for the motivation, first of all, since we're not data scientists here, as far as I can tell, let me just very briefly explain what data scientists typically do to produce an ML model. So there are, this is from Microsoft Research, by the way, they explain how they work internally. So I have pointed out here three, let's say, group of tasks. First of all, it's everything related to data, where to gather it from. Maybe it needs a little bit of cleaning, do some labeling if the labels are missing. Then there are the main tasks related to training the model, basically. And then it's after you train it, you need to deploy it to some kind of model inference server to serve predictions for other services that request. And the final step, and the one that we focus on, is the continuous monitoring to make sure that the model performs as expected. And this is important because some problems might happen with the model over time. So I introduced like a very simple example in the paper that has to do with just a theoretical call center that receives calls from customers, and then we would like to predict whether the customer is happy with the service or not based on how long they waited in the queue to talk to someone, and then how long they waited they spoke to someone. So over here are all the happy customers, over here are all the unhappy customers, and the machine learning model, looking at this data set, extracted this decision boundary, so to segregate the happy from the unhappy. So this is the training set, but over time, due to changes in customer attitudes, or perhaps someday the call center is understaffed, so everybody now waits more on average than what used to happen in the training set. So all of these scenarios are in the literature called dataset shift, and depending on what kind of shift, there's different terminologies such as covariate shift or concept shift, and so on. So all of these scenarios we would like to detect and mitigate it somehow, maybe retrain the model, or at least send out an email notification so that data scientists can take a look to determine what has gone wrong. Now, the problem with that is that it's not so easy. And and most companies that work with ML a lot point out that actually the actual machine learning related code is just a small part of the overall system. For an ML-based system to work, it needs many different components, such as serving and monitoring. So in order to develop all of these components, usually data scientists need to cooperate with software engineers. They cannot do everything by themselves. And now the problem is that because of this cross-discipline communication, it introduces some overhead, some misunderstandings. Sometimes a software engineer has to receive the specification of what to do with the monitoring from the data scientist, but they're not data scientists themselves, so it's a little bit difficult. So in order to address these challenges, we propose the following system. This is the gist of it to explain who does what. Okay, so first of all, we have the ML platform. So all of the components that are used to store data, use them to train models, and host the models themselves and serve predictions. So these platforms are developed and maintained by software engineers, and data scientists use them to train and deploy their models. These models, as I said in the beginning, they are used to serve predictions for other applications, but that's outside our scope. And then, us as language engineers, we develop a domain-specific language called PDL for Panoptis Description Language. Panoptis is the overall name of the project. And now, and also for this domain-specific language, we develop an execution engine. And I will explain what this execution engine does. So data scientists, after they deploy the models, they can use our DSL to create monitoring workflow models that explain how the models need to be monitored. These DSL models are sent to the execution engine, and now the execution engine interfaces with two parts. First, the ML platform, because it needs some information about what is going on with models. For example, whenever the model serves a new prediction, an event is sent from the ML platform to the execution engine. And with this information, the orchestrator, taking into account the workflow specification, sends itself events to the so-called platform-specific components that execute the shift detection algorithms, and when shift is detected, mitigating actions are taken. And for this, the platform-specific component, which also is developed by software engineers to because we need to know something about the ML platforms, and different ML platforms do different things, but the interfaces are standardized. So the same orchestrator can be used with multiple ML platforms and multiple platform-specific components, as long as the formats of the events are followed. So this is the overall idea. And we will now explain the language a little bit. So for the language, first of all, we need to have some information about what models are deployed and what features they receive to produce predictions and things like of this nature. So this is some classes in the meta model that handle that. This is not specific to dataset shift, but just as a starting point, so that the execution engine knows what exists in the ML platform. On top of that, this is the classes, the main classes related to the monitoring workflow specification. So the most important concept is the segregation between algorithm and algorithm runtime. So the algorithm here is the what needs to be executed to detect the shift. And for this, we have separated the algorithmic aspects from the technical aspects in a way similar to like function as a service, as if you have seen it, for example, on cloud platforms, where you just provide a small function with your business logic, and then the runtime takes care of other technical aspects like load balancing or high availability and stuff like that. So similarly here, the runtime is developed by the software engineer and does things such as data collection, and then the data scientist only has to provide the algorithmic part. This is the main selling point of this solution. And then similarly, we have some meta model classes to represent the actions that are taken when shift is detected. And lastly, we have, of course, the scheduling. So what is the frequency that data scientists would like the algorithms to be executed, and so on. So there are multiple ways to schedule these executions based on time, based on, for example, how many samples the ML model has served. If we have ground truth data available, it's also a way to trigger the shift detection. And then in terms of user experience, we developed a web-based editor based on using Xtext. So it's a textual concrete syntax, and data scientists don't need to install anything. They just use their browser, and it supports things such as syntax highlighting, error highlighting, autocomplete, and everything that Xtext supports. And moving on to the evaluation. So to evaluate this solution, we conducted an empirical study with 3 parts. First of all, we gave the 10 participating data scientists a PDL model in the textual format, and asked them 15 comprehension questions to see if they understand what the PDL model expresses in terms of the meta model. And after that, we gave them some hands-on tasks with a demo system that we developed that I'm going to show later, to see if they can use PDL to deploy monitoring workflows and detect shifts. And then we gave them a questionnaire to ask them if they consider the solution useful. So on with the results. So in terms of comprehension, every participant did very well. Most questions everybody got right, and then for some questions there were a couple of participants that were did some small mistakes. So for the hands-on tasks, we implemented a simulator that simulates this call center example that I introduced in the beginning. So the users could change some parameters of the simulation to, for example, make the customers more patient, less patient, or put more workers in the call center, less workers in the call center. And these all affected, for example, the waiting times and whether the customers were happy or not after the calls. And the second dashboard were used to visualize the results, like call time, wait time, service times, what the model predicted, and so on. So we asked participants to complete 5 tasks. Most of them, again, they did pretty well. And lastly, for the evaluation, we asked them to evaluate the solution based on various metrics. Some of them had to do with how easy do you think it is to use the solution, or how much do you think it's going to help you with your everyday work. And again, it was evaluated pretty favorably. And then, because this example was very simplistic, we also went ahead and used some external open source ML models, such as an image classifier, a system that recognizes speech and transcribes it to text, and third, the ML model that does credit scoring. So different models with different input and output modalities, so images or sound or tabular data, and so on. And we were able to support all of these types of ML models. So it goes on to show that yeah, the approach is quite flexible, because the execution engine doesn't actually need to know the specifics of the machine learning model. It just reacts on events from the ML platform and then sends events out. It's all event-based, and every service is decoupled. So these are the main things that I wanted to talk about, and we can just go to Q&A. Thank you.